In this video here, we're going to take a look at first order differential equations. So by using a suitable substitution, we can reduce a first order differential equation into a form that we can solve, either by separating the variables or by using an integrating factor. So before continuing with this video here, just make sure that you're confident with solving integrals by separating the variables, which we covered in A-level maths, and by using an integrating factor, which we covered in Core Pure. Okay? So I think the best way to demonstrate this concept here is to just run through a couple of practice questions then for reducible first order differential equations. So let's just get started here then with question 1. Now as we can see for question 1 here, right, split into 3 different parts. So let's begin then with part A here. So for part A then it says use this substitution here, so z is equal to x plus y, to transform this given differential equation here into this differential equation here. So to get us started then, hopefully you might be able to recognize here then that dy by dx here, so x squared plus 2xy plus y squared, is just the same here as x plus y squared. Okay, so x plus y squared here. And just notice as well then that our substitution here, z is equal to x plus y. So if I've got x plus y squared here for dy by dx, that's just the same then as z squared. Okay. And let's also just consider here then the original substitution. So z is equal to x plus y. Okay, so z is equal to x plus y. Now we want dz by dx here, right? So dz by dx here. So let's just differentiate z here with respect to x. So if we do that then, we get dz by dx here is equal to 1 plus dy by dx. So 1 plus dy by dx here. And at this point here now, part A is pretty much complete because we know that dy by dx here is z squared. Let's just replace dy by dx then with z squared. So dz by dx here is equal to z squared plus 1 as required. Okay. And there we have it. So that gives us the solution to part A. Hopefully nice and straightforward there, just to get us started. Now for part B then, it just says, find the general solution to the original equation. Now if we want to find the general solution here to the original equation, all we need to do here is solve this differential equation. And we can just do that then by separating the variables. So on the left-hand side here, what I want is just anything in terms of z. On the right hand side here, anything in terms of x. So what I need to do here is divide both sides by z squared plus 1. Okay. And don't forget then that we also integrate both sides as well to solve the differential equation. We have the integral then of 1 over z squared plus 1 dz is equal to the integral then of 1 dx. Okay. So what you need to recognize here then, that 1 over z squared plus 1, or the integral of 1 over z squared plus 1, this is one of our standard results here, right? So this just gives me arctan of z here. So I get arctan of z, and this will be equal to x plus c. Okay. And now just replace z then with the original substitution. And therefore we obtain then arctan, so arctan of x plus y is equal to x plus c. Okay, and there we have it. So that gives us the general solution to the original equation. And now finally then for part C here, what we want to do now is find a particular solution. So we want to find the particular solution for which y equals 0 when x equals 0. So all we need to do now is just use these conditions here, okay? So arctan of 0 plus 0 is equal to 0 plus c. So let's just make a note of that here. So arctan of 0 plus 0, so that's just 0, right? But I'll write it out in full, is equal to 0 plus c. So what I'm doing here then is just solving to find our constant of integration here, right? Plus c. And as we can see then, c is simply 0. Okay, so what that means then is I've obtained now arctan of x plus y is equal to x because c is simply 0. So therefore, arctan of x plus y is equal to x. Okay? So what I want here then is y equals f of x, right? Some function of x here. So what I'm going to do here then is get rid of the arctan here, right? So tan of arctan gets rid of the arctan here, which would just give me x plus y here on the left-hand side. So x plus y is equal to tan x. So I've just took tan of both sides here, like so. And then basically, as we've just mentioned, we just want y equals here, right? So therefore, y is equal. So all I need to do then is just subtract x off both sides. So y is equal to tan x minus x here. So tan x minus x there, okay? And there we have it. So this here then is our particular solution for which y equals 0 when x equals 0 there, okay? So there we have it. That gives us the solution to question 1. So to finish with here then, let's just have a go now at the very last question. So as we can see here then, we have question 2, and question 2 is split into 2 different parts. We've got part A and part B. So let's begin then with part A here. So all I want to do to begin with here is use this substitution to transform this given differential equation here into a differential equation in u and x, okay? Now this is a little bit different to the previous question because for the previous question, you was given the desired differential equation. For this question here, that's what we need to deduce ourselves, okay? So a little bit trickier here. We're not kind of given a little bit of a guide as to where we need to get to. We just need to obtain that ourselves, okay? So to begin with here, let's just start with the original differential equation, okay? We want to rewrite this using this substitution. So basically, wherever we see an x minus y, let's just replace that with u. So straight away, within the numerator here, we have x minus y. So replace x minus y with u, we obtain u plus 1 here for our numerator. And doing the same here then with the denominator, again, we have x minus y. So replace that with u, and we obtain u plus 2 for the denominator, okay? What we also want to consider here then is the original substitution. So u is equal to x minus y here, okay? Now if we differentiate u here with respect to x, that would give us a differential equation in u and x here, okay? Once we substitute for dy by dx, of course. So du by dx here, nice and straightforward then. This would give us 1 minus dy by dx. And now by substituting this expression here for dy by dx, we will obtain a differential equation in u and x, okay? So let's substitute for dy by dx here then. So in that case, du by dx. So du by dx here is equal to 1 minus dy by dx, which is u plus 1 over u plus 2. So u plus 1 all over u plus 2, like so. Now for the right-hand side here, let's just get this over a common denominator. If we do that then, what we'd obtain here is u plus 2 minus u minus 1 all over u plus 2. Well, straight away, we can cancel these u's here, like so. 2 minus 1 gives us 1. What we obtain here then is 1 all over u plus 2. Okay, so this here then is for du by dx. And that gives us the solution then to part A. Okay, we have now a differential equation in u and x here. Okay, so that's part A complete. Let's have a go now at part B. So for part B then it says by first solving this new differential equation, show that the general solution to the original equation may be written as this equation here, where c is an arbitrary constant. Now for part B here, this is actually pretty straightforward. In fact, it's more of an A-level maths problem than an A-level further maths problem, because all I want to do here is solve this differential equation here. So du by dx is equal to 1 over u plus 2. And the way that we're going to do that then is by separating the variables. Okay, so for part B here, let's just separate the variables. So in that case then, anything in terms of u will be on the left-hand side. And don't forget we take integrals of both sides here. I've got the integral then. If I've got du by dx equal to 1 over u plus 2, to get anything in terms of u on the left-hand side here, I need to sign through by u plus 2. So I get u plus 2 du on the left-hand side, like so. And this is equal to the integral then. So the integral here. And on the right-hand side here then, anything in terms of x. So all I get left with here then is 1 dx. Okay. So now let's just evaluate these integrals here. Again, pretty straightforward, right? So again, it's just basic A-level maths here. I get u squared over 2. So u squared over 2 plus 2u is equal to x plus c here. Okay. And at this point here then, wherever we see a u, let's just replace that with the original substitution. So what I get here then is a half x minus y squared, like so, plus 2 lots. So 2 lots of x minus y is equal to x plus c. Okay. Now I notice here then that the coefficient of x minus y squared is 1. My coefficient here for x minus y squared is a half. So basically all we need to do here is times through by 2. So I get x minus y squared. I then get 4 lots, so 2 times 2 is 4, so 4 lots of x minus y is equal to 2x plus 2c. So 2x plus 2c there, okay? So let's just expand here and simplify them. I get x minus y all squared. So this here then, this would expand to give us 4x minus 4y. I've got 2x here, so if I've got 4x and I subtract 2x here, that would give me 2x, so plus 2x there. 4 times minus y is minus 4y. We can't do anything else with that, right? So I just get minus 4y there. We've dealt with the 2x, right? We subtracted that off both sides. And then finally, I've got the 2c here. So let's just subtract 2c off both sides. So we get minus 2c is equal to 0, okay? And notice here then, this is exactly what we wanted, right? So as required, and question complete. So as required there, and question complete. So there we have it, right? That gives the solution to part B and the solution to the very last question, question 2. So that brings us to the end then of this video here on reducible first order differential equations.